it will be a little bit boring because so much mathematical concepts are there. But it is just a short overview I'll be giving because most of the items is already been covered by Professor Kumar. So here my primary focus will be on how the finite volume methodology can be applicable for radiation heat transfer and along with other mode of heat transfer also combined conduction convection radiation like that and along with other mode of heat transfer combined conduction convection radiation like that and along with other so start this combined so let me just conduction overview just a short overview. So start like radiation participating medium, which you are already aware of. Professor Kumar like radiation participating medium, then you will see some mathematical similarity between our conventional CFD problems based on convection diffusion system and our radiation transfer. So what is similarity? So that the appropriate numerical methodology can be applied to solve the RQ. So that it looks little different mathematical methodology. The approach is also different. But how our existing CFD techniques can be applicable for solving this unique equation of radiation transfer that will be discussed here. Then some of the existing methods I'll be talking about, like the flux method, then the discrete ordinate method, which is quite popular since the beginning, and then it becomes the finite volume method. And later on, it was realized that all these methods whatever existing, so these are all can be derived from finite volume methodology. So the basic background framework what is required for solving different transport equations using finite volume method, that will be our primary focus in this short lecture. So then we will cover some introductory part of radiation other mode of heat transfer. So then we will cover some introductory part of radiation other mode of heat transfer. So coming to radiation participation here. So this is your RT which you are already aware of. So I have given the total T RT including the transient part. So transient part sometimes is applicable for ultra short time scale entities. Right. So here you can see this is significant ultra short time scale phenomena because you see the denominator term, there is a term called c, which is the speed of photon travel. So which is the light speed. So you know how fast the light moves in the medium, right? So then if the time scale of our observation is not so small, then we cannot visualize any transient effect on photon transfer. So that's why it has only significance you can find in ultra short time scale phenomena. Like if you go sub nanosecond or microsecond, then this term is quite play a major role, like some kind of laser application. So then comes our other means what are the phenomena going on which is already been covered by Professor Kumar, like absorption and outscattering. Absorption, emission and scattering, these are the three fundamental phenomena outscattering happening based on absorption, emission, radiative energy balance. This is for a particular pencil of photon ray, right? And then we will cover this another is the emission, because sometimes the medium may emit also. So the emission is a augmentation term, so that's why the medium may emit prefix to plus. And this emission is particularly based on temperature of the medium. So any temperature above absolute 0 Kelvin, this emission is the medium is ready of the medium. So any temperature above absolute, and then The last term, which is the most critical term in Earth, if this should not have been there, then handling this equation would have been quite easier for us, because then it would be just a ordinary differential equation. So this is the in-scattering term, which creates a lot of traffic, and then because of that, so many methodology. So this is the in-scattering term. So this is the in-scattering term. In-scattering term basically it refers to if the photon is coming from all other direction into your direction of travel of interest, that will contribute. So that's why it is an augmentation term. So it increases the photon intensity. So then whatever outscattered from other point of the medium, which will come into your direction of interest, so that will add as a in-scattering. Which will come into your direction of interest. S is the direction. S is the particular direction, because this relative energy balance equation, what you see, that has been developed for particular pencil of energy balance, bulk of photon moving particular certain direction. Particular pencil of energy balance, bulk of photon moving particular certain flux the CD similarity. Because before we handle this complex integral differential equation, we have to see the similarity between conventional CFD techniques, which is applicable for solving like your diffusion as well as convection problems. How we can handle the diffusion as well as integral differential equation using that CFD concept, which is valid for convection diffusion. Integral differential stands for convection. CFD concept. So you can see that the convection diffusion equation is shown for two-dimensional system. So here the first term is our transient local transient system term, and the second term is your convection term. Then the right hand side the diffusion term and the source term as there. So if you look at the RT also, it looks very similar mathematically. Like it has a transient term, right? And it has a this convection like term. Although there is no convection like term, there is no flow, but there is a convection like term is there. And then you have a source term there. So this similarity you can find that you can make this transient term of RT is very similar to your convection diffusion transient term, right? This transient term at least in similar form. And if you see the convection term in our original heat transfer fluid flow problem, which is quite mathematically similar to our RT, that is quite the special gradient of the RT dx. So where this mu and xi refers to our direction cosine, that I will show you later. Right? And then we do have a source term like this. So this source term, you see that S is also can be similar format like minus beta I plus S, whatever is also found in R. So this S minus beta I plus S can be a nonlinear source for our conventional transfer problem that can be linearized in the format like there is a constant part of the source term and there is a linear format of the source term S. So if you compare this SC plus SP5, then it is very similar to like your SP can be now you can say it is nothing but minus beta, which is equal to extinction coefficient, right? And then source is our radiative source, which consists of our emission term as well as our in-scattering emission term as well as in-scattering. If you see the similarity, like there we are calculating the temperature for our conventional fluid flow heat transfer problem, and phi refers to our temperature, and here phi refers to temperature or any kind of enthalpy, species whatever, depending on type of problems what you are dealing with. And here it is only serrated intensity. Depending on type of problems what you are dealing with. And here, so what is our observation from this mathematical similarity? What you can see, like there is no diffusion like term in RP. That this you can set gamma, the diffusion coefficient, to be 0 for RP. So that is, of course, simplifying our problem by solving the RP 0 for RP. And so that is looking at this mathematical similarity, so we can apply all these basic principles of developing good numerical methodology for solving these kind of complex transport. So that rulers of CFD, whatever solution methodologies so far have developed or people are trying to improve upon different methodologies, they are solely based on this conservativeness property, then boundedness property, then transportiveness. So conservativeness, any kind of conservation principle can be applied. Conservation of energy, mass, momentum, like that. And boundedness means the solution must be bounded. Means solution should not shoot up. Means it should not be unphysically in it. While we simulate, it should not give us any unphysical result. So that's why while developing a numerical methodology, we must ensure that the method should be bounded. Means the result should be physically plausible result should be predicted from our numerical method. And another is transportiveness. This transportiveness feature is something like, let's say, the transportiveness feature means some flow kind of phenomenon. Transport means something is flowing. So here, like in our conventional flow heat transfer process, the flow is happening. The heat is flowing because of the actual flow in the field, like U and V component or convection diffusion refers to the flow field. And here, this transportiveness feature you can find in our U and J, these are called direction cosine. In which direction the photon is also traveling. But of course, for U and V, you have to compute in your flow field the momentum equation. But here you do not have to. It is the fixed value because you have to predefine your direction, in which direction you want your photon to travel. Okay, so that's why this mu and J, which is simplified form of our convection diffusion equation with a constant velocity. Prior to know the flow rate, then you want to predict the temperature distribution. So these three features are quite valid to develop a methodology for our radiative transfer equation. Then coming to the first method. So that is the very first method, longest 97 time people have developed Flax method. So this simplifies the original problem to much extent because in original format it is quite complex because you can see the actual radiance intensity distribution is like that. So there is intensity, this arrows what you see, these are all different bulk components when you see right? And their intensity maybe their length basically defines the intensity magnitude, right? So lower length means short arrow means quick intensity, larger size arrow means larger quantity of photons are traveling high intensity. So in different directions you have pretty very unstructured format it is there, right? But what the Flax method does is that and this intensity distribution is spherical in nature. Means in the total sphere in different directions how the intensity varies that has been shown in the left figure, and in the right figure you can see the different approximation that we convert this total spherical intensity to two hemispheres. And in one hemisphere you have uniform intensity, and in the other hemisphere you have also uniform intensity of different magnitude. So that means basically we have two magnitudes of difference in two different hemispherical directions. Right? So that has been shown here, like here. I plus for positive coordinate direction and I minus for negative coordinate direction. And for positive hemisphere we have this the radiative transfer equation can be written like this, because radiative transfer equation for positive hemisphere it has to be integrated, and then after integration you will get this kind of an positive hemisphere. So for positive hemisphere this will for negative hemisphere and this kind of an hemisphere. So the Flux method, what is our observation is that it divides the angular space into two solid angles, and the magnitude of the radiant intensity is constant in each solid angle. That is what you can see constant, like all the intensity positive hemisphere or negative hemisphere is constant magnitude of intensity. And this approach reduces the RT to two ordinary differential equations, which can be solved using any convenient method. And what is our remarks on this method is that the method would not accurately model anisotropic scattering. Anisotropic scattering means the scattering in different directions are different, depends on in which direction bulk of photons are moving, what quantity that is defined by that is not uniform throughout the spherical disk. So with two centimeter discretization practice it is very difficult to capture anisotropic scattering. Then comes our U method, that is our discrete coordinate method. So since people have faced this problem to address the anisotropic scattering, they look for any alternative methods. Then our one of the very well-known Indian scientist Chandrasekhar during his research tenure in USA, he developed this discrete coordinate method. So the actual radiant intensity distribution is looking like this. And on the right hand side figure you can see that the discrete ordinate method approximation is there. Every ordinate direction you can discrete the intensity and solve for it. Then you will get the actual magnitude. So discrete in nature. So the discrete nature of photon travel can be very well captured in discrete coordinate method. And for RT, how we can write discrete coordinate method? Same like this. The L stands for and this part is your in scattering part, where this W is the quadrature set. So different directions you have to certify certain moment principle to find those different ways. So that is the primary focus of the U method. And what are the features? Features is that there is no solid angle reference in discrete coordinate method, because there is no concept of solid angle in discrete coordinate method. And the angular direction carry principle which is arbitrary. And the quadrature sets the ordinate directions and angular weights can be developed that integrate the radiant energy and weights. So that weights can found out. So people have the data set is available for different quadrature sets for different ordinate directions. So people have the data set, and then using those tabulated data you can simulate the ordinate directions. And the remarks what you can get from this discrete ordinal method is that the accurate calculation of several discrete singular weights satisfying the full half-range moment are computationally challenging for certain configurations. Let's say if you have a moment configuration, then this finding those angular quadrature sets are quite computationally intensive. So that makes that limit the applicable quadrature sets are quite computationally intensive. So then comes our so what it does? It completely removes that requirement of finding the angular quadrature set, but there is the discrete requirement of finding the parabolic method. So it is quite a popular method for solving CFD problems. So have anybody been exposed to CFD earlier for solving CFD problems? So then you can understand the methodology what we'll be discussing about. But for a beginners also, I tried my best to explain the thing. Some of the is not there. I'll share my best to explain the thing. So the domain discretization control angles, the angular space, because in radiation you have a along with the spatial domain, you have an angular domain is also there, right? Because photons are traveling in different directions. So that directions have to be direction domain has to be taken into account, like our azimuthal angle and our polar angle. So total azimuthal angle is 2 pi and total polar angle is pi. That constitutes the full sphere angle. So value solid angle value is 4 pi. And the control angle, control volumes for geometrical space, which is quite extensively used for our conventional CFD. The calculation of angular weight as required in DOM is avoided. It is completely you can avoid calculating directional weights because we have developed the concept of control angle, and based on that we can still compute our equivalent angular quadrature set based on our distribution of angular. It is based on conservation. The central idea of getting this kind of volume method is popular because it is based on conservation. So you can easily check the methodology performance by looking at the quantity what you are measuring, whether it is conserved at any arbitrary spatial location. So that is the beauty of this kind of concept. And then we do have a concept of control angle. So that control angle shown here. Control angle. So this is our control angle, and that can be calculated from the angle. And theta and phi are our theta is the polar angle and phi is the azimuthal angle. Azimuthal means this one and polar means like this one. Okay, that constitutes the full azimuthal angle. So the polar angle span is 0 to pi and the azimuthal span is 0 to 2 full circle. Okay. Then you can constitute the azimuthal span is 0 to 2. So you can create your control angles as per your requirement or as per your requirement in the based on your geometrical shape. That is quite flexible. Here the control angles quite flexible. Here then the actual intensity. Then we will see that how FDM will take care of the actual intensity distribution. The actual is this one, but then every point will apply different control angles. So in each of the control angle, the magnitude of intensity remains constant. So then, depending on the your actual intensity distribution, the more number of control angles you create, the more distribution of intensity. So you can resemble the actual intensity distribution quite easily using Hannon control angle generation. Right? Like here I have shown you one of the figure. Here the number of control angles are 4 control angles can be shown here. So each control angle you have a different 4 control angles. So if you are expecting that there will be large variation in intensity direction based on your boundary conditions, then you can create more number of control angles. That is the flexibility you design. And the two-flex method is something like you can now say that two-flex method is the subset of finite volume method. It is a special case of finite volume method where you have only two control angles, right? Two hemispherical control angles. If in a finite volume method you are generating two control angles, then it is nothing but a flux. So that has been shown here, and then discrete coordinate method also can be obtained from finite volume method. In each discrete direction is captured with control angle, and you integrate that control angle with a delta function. Means within this control angle, in a particular direction only, the intensity is available. In other direction, within that control angle, not available. So that if you apply that principle in your finite volume method, it will automatically gives you the result of here. Right? And intensity is assumed within a control angle. That is our primary features of the finite volume method. And then you integrate this equation because it is based on conservation principle. So that's why the first step in finite volume method, you have to integrate the equation based on using a finite volume. Because whatever differential equation you have seen here, that is basically coming from this conservation principle only. And that conservation principle now we are applying with finite volumes. So that's why it's finite volume. So how do you get this finite volume conservation? By integrating this, the differential equation which is valid for infinite small size of the control volume. Now you have to integrate it for a finite volume size. Then you will get the conservation for within a finite size of the volume because of our ease of computation. Because computation can only possible with finite precision. That means because your special finite volume size should be finite computation, not infinite size. You cannot get finite no, it is just I have shown here the 4 control angles. It is up to you. If the actual intensity distribution let's say quite arbitrary, then you can create as many number of control angles to resemble this arbitrary. Then you can create as many number of control angles to resemble this arbitrary. No, we are integrating over a small control angle. We are not integrating over a whole sphere. We are integrating over a small control angle. And then we are again right, and that's why we are saying that within this small control angle, our photon intensity, right? And that's why we are saying that is the primary feature of the control angle. And how many number of control angles you need, that completely depends on your actual intensity. How many number of control angles you need, that completely depends on your actual intensity. No, that is the span. Means the domain size, angular domain size. Angular domain size, theta like polar angle, varies between 0 to pi, and the azimuthal angle varies between 0 to pi. And that have to be discrete. Like our spatial domain, azimuthal angle varies So the two, let's say theta will divide discretely 4 number of control. So that means pi by 4. And then it will divide the azimuthal domain into 4 number of control angles. Then it will be 2 pi by 4. Like our domain in the discrete and 4 number of the same thing like our angular. But here our angular domain it cannot change because it is spherical always angular. So our polar angle domain size is always pi and our azimuthal angle domain is also 2. Then it creates the full spherical and our azimuthal angle domain is so okay. And then the first step is to integrate this RT for a finite size control angle. So this is the concept of control angle now developed. Earlier that has not been used in flux method. Now when the finite volume method has been developed, then this flux people thought that it is we have already developed the finite volume method, but here we have written only 2 control. Right? So if there are 4 number of control angles, then you can go for finite. Right? So if you right. Yes. For each control angle, you have to calculate those values of mu and for each direction control angle, because the span of this theta minus theta plus phi minus phi plus will be depending on the control angle side. Right? Theta minus theta plus phi minus phi plus will be depending on the control angle side. For our, this is just for a simplified case like 1D system. So you can integrate this. This is just for a typical control angle delta omega L. L stands for our particular direction. Typical control angle direction. Here what we have to L stands for our particular direction. So here delta control angle that from our here what we have with variation and phi then we go and phi. So then after integration you can see that the direction cosine term then after integration is z. See that so this is z nothing but our direction cosine term. So this direction cosine is calculated for a finite size control angle as this NZ dot calculated to d. And what is this escape direction? Somebody was asking S. Na? So this S is this one, the direction of travel of the output. Somebody was asking so S. In our Cartesian system, we can show like sin theta cos phi, ES and sin theta sin phi. This is our standard condition. But it is up to you because we have measure our theta from positive z axis and phi from positive x axis. That's why measure our theta from positive z axis. So remember, that's why I am emphasizing here radiation is always 3-dimensional. Although I am talking about 1D system, this 1D only refers to spatial domain, not angular, because angular is always digital. So that refers to spatial domain. So this is the direction cosine that you can calculate. That is spatial. So that constitutes our angular quadrature set in DOL. What we said. But in DOS, you have to calculate and satisfy certain moment principle. But here, in principle, you are generated on the control angles, and depending on your fundamental side, your weights can be different. Which depends on your direction cosine. And depending on your fundamental side, your weights can be different. And for our one-dimensional system, we take EZ direction. We can take that. And whenever we are talking about 1D system in our means radiation direction along z direction we will consider. And for 2-dimensional system we take x1 along z direction here we will consider. And for 3-dimensional all x1. Then our then second part later on this has been linearized. So this linearization principle is done by Patankar Group. So my advisor, my PhD advisor, has developed this linearized form of that during his PhD tenure. My advisor, my PhD advisor. So this is something very interesting to see that the extinction coefficient, what you see here, this linearization is actually required because of this coefficient. And then creates the traffic for solving this or handling this. If this would not happen there, then much easier for solving this. So this here, whenever you are talking about, let's say I want to know my photon in this particular direction. So when I will calculate the incident part, that direction is also good. But I am not sure what is my intensity in this direction. So then how do I calculate this? So that's why this my advisor can't split this part. He split this part in two parts. One is modified extinction coefficient, another is modified source. Right? So earlier it was only source. Now it has been split in two. Then in this modified source, this direction of interest in our chosen direction is not modified source, then it is very easy to solve this numerically because you do not have to guess many intensities. Otherwise, you have to guess it and then again recalculate. So it consumes a lot of iterations and computational time also. So that should be our primary focus. Patankar always says that we must minimize the computation. Then only things can be realized. Otherwise, you can create complex problems very easy but very difficult. So that's why we must ensure that it consumes less iterations, less computational cost, based on which we can get good results. That should be our primary subject. So what is that? Based on which we can get good results. Then our linearized RT can be looking like this. So there is again transientia and there is partition and there is augmentation. So there is again augmentation. So this is the modified. Now this modified does not include the component. So this is the modified. Now this modified does not include the component. So this is explicitly written L prime not. So this S and L component does not consider L prime. So then you do not have to guess the S and L component, that is the primary advantage. And the advantages of linearization is that one of the very important advantage here is that the effective optical depth reduces. Because although our physical dimension we are discretizing, but in radiation problems it is actually the optical dimension. That dimension the extinction coefficient times the physical dimension. Which are this beta to the physical dimension, the optical dimension. So since our beta now reduces physical dimension, you can see that this beta is now smaller than the actual beta. Our modified beta is now smaller than the original beta. So our optical dimension is reduced. So then what is our advantage? The pure control quality because now domain size change means reduces. Although the physical dimension is there, but optical dimension reduces. So then you need fewer number of control points to get it, and then computation is faster. So it reduces our computational cost. So that is one of the very important disadvantages. And faster conversion is because less gas intensity requirement for computation. Because now this SML does not include the L component. What we will do for this SML does not include the L component. Then our FBM formulation again which is based on conservation principle. So you have to integrate for a finite size of the control formulation. So that will give rise to and to find. So you have to integrate. Then the second term in order to simplify the second term, we utilize this dimension here. Then the second term we utilize and the transient draw dimension. Then the second term we utilize transient draw dimension. Our class term simplification, like after applying the constant here, our class term simplification, like this applying the constant, and then finally we can get attenuation of terms. What we are saying, whatever average value, because all these values what you see, like what we are saying, that I and S and beta, because this P refers to the average value we are storing at the center of the C, so that we will get good accuracy. That is basically the region where you are storing at the center is that is second order accurate, so good accuracy you can get. The region where you are storing at the center, this average value you are storing, so good accuracy you can get. And then similarly, the name discrete are then we have a special for a structure is like this. So we have a boundary units are also there. Just a particular we have a zero control value by the boundary to handle the boundary just one particular and then you have unstructured value there. And then you have the impedance amount because that is always fixed. The span of theta and phi, that means phi and 2 because that is always fixed. The span of theta and then we have control angles, control volume standard and for a 2D control angles, control like north, south for a 2D control. Okay, similarly you have a control angle size is also there, and then you have a control angle in your special control angle size is also there, just like a and then conical section. So each cone represents a control angle size is also there, and in a particular control angle intensity adjudicated once, and that is the average intensity comes out of this control in a particular center of the intensity adjudicated. So then the finite 2D two-dimensional and density equation now we can like so whatever direction constant you see, these are all in the quadrature set in discrete coordinate class. So whatever direction constant you see, these are all in the quadrature set. Then our modifier is coefficient and modifier system, and then while solving this equation, because we have so many unknown terms are there. So what we do, the step scheme is very similar to our upward scheme in our connection problem, safety problem. So that has been applied. Very similar. Means upstream value prevails. So like for this particular configuration, you can see that the facial intensity corresponds to so for this I facial intensity will be equal to I because the upstream is and for this the upstream is definite and for this again the upstream and for this upstream and for this like this. So that's right. So we see this and that and finally it's standard form limited like this. So that's right. So where other terms here and then we do have a compact form of the RPE also there, which can be solved irrespective of different directions. All the coefficients, remember, all the coefficients are not exhibited of different directions at a time, because depending on the direction, some coefficients exhibited, some coefficients direction. So that's why, because depending on the direction, some coefficients. So this is the standard time development. Compact form of the equation, and how do we solve it? At each time step, an identity method is used to solve the relative set of equations. A marching order can be used can be employed to efficiently solve the fate of algebraic equations, because once you start from the boundary information is known to you. So you can carry on based on the upstream values and go on computing the whole domain. So standard CFD solution method like PDMF, which is quite popular in solving CFD problems, not necessarily required here for solving the RP, for solving the high volume based discrete RP, because it is simply based on march. So once you march from the boundary, all the values are known. So you do not need a methodology for solving the discrete, unlike the discrete. So that is the select advantage. And then coming to our radiation, other mode of transfer, how it is handled. This is our conduction plus radiation example. Professor Kumar was showing you the radiation source term. So that radiation source term is here. Professor Kumar was showing you the radiation source term. So how do you evaluate this radiation source? This radiation source is transient format. But of course, remember this term is quite valid when you are going for very ultra short time scale. Otherwise, this is quite valid when you are going for very ultra short time scale. Which is the absorption coefficient by IB. IB is the black body intensity minus G is the irradiation. So, black body intensity minus G is the irradiation. Why? Because it is looking like what you can say here, it is the conduction term. Like if you see the conduction term, what you can say conduction, this will be nothing but conduction term. Like if you see the conduction term, so now the Q is, because it is conduction plus radiation, so Q is QC plus Q1. So actually it is minus del dot Q conduction plus radiation. So del dot QC minus del dot QC. And this minus del dot Q1. So del dot QC minus del dot QC. So in order to solve this transport equation, we need the radiation information now. So that radiation information can be obtained. Radiation information unknown here is the information. The G is the unknown. So G can only be obtained when you have a intensity field everywhere inside the room. Because G is the radiation which is calculated intensity of IT. Okay, over the whole system. So then, remember G does not depend on X. G only depends on spatial location. Because G is the contributory effect of intensity from all the directions. Because G is the spatial location. So that's why first you have to calculate this G, then only you can find spatial, and then so that is the one thing you have to calculate so then you can find the temperature inside the furnace. Like in your combustion model, when radiation is also included, find the temperature. So first we have to solve for the RT as we have discussed using Heisenberg method. Once your RT is solved, your intensity distribution is known at every location. Then the G value also spatially known. So once this is shown, you can then find G dimension. So then you can put in the source term, and this source term you take it to the standard linearized form SC plus SC1, then you can find so that is the standard practice we follow. Similarly, if you go for convection radiation along with the phase change also, we are now working on how radiation affects the radiation along with the phase change. Then you have a convection term, like our convection phase change equation. I have shown you a slide. So there is a convection term that convection phase change equation. I have shown you. So there is no more change. Conduction convection and conduction convection. Only so there is no more change. and then rest of the things are quite known. Okay, and this equation can be solved using conventional CFD technique. Those who have not exposed to CFD, of course, then they may be new to that. But of course, time is a constant, so we cannot discuss much more about this. But if you need it, I have the solution methodology for conventional CFD that I edit. That is fine. Okay, that's all from me. So our formal technical session now over. So we can. So our formal technical session